In this video, we'll learn about linear inequalities in one variable. Starting with some definitions, we first need to go over the inequality symbols. So we have 4 inequality symbols that we'll be looking at. The first one, when you see the symbol, you read it as is less than. Next, if we turn that symbol around in the other direction, we have is greater than. Thirdly, we have is less than or equal to, and last is greater than or equal to. Now the first two are called strict inequalities because they only represent the case where one value is less than the other or greater than the other, and the other two are non-strict because it does involve the case where two quantities could be equal to each other. Now, if we have a linear inequality in one variable, this is just a statement of the form ax plus b is less than 0, where a and b are real numbers, a is not equal to 0, and this less than can be any 4 of these inequality symbols. So you could replace this with greater than or equal to, or greater than, and it gives you just a different inequality. Now, we first need to talk about how to represent inequalities in several different forms before we could go on and solve them. So we have really 3 representations here: inequality form, graphically, and a new notation, which may be a new notation for you, called interval notation. Alright, so we have 3 types. And in all of these definitions, a and b are real numbers, a is always less than b, and x represents the variable. So in the first case, we have what's called a closed interval. And as an inequality, that means that x is between a and b and can be equal to a or equal to b. So as a picture, we're thinking of a snapshot of the number line. And here a is on the left because it's less than b. And x can be either anything in between, so we have the shading in between, or it can be equal to a, so we have a bracket at a, or equal to b, so we have a bracket at b. Now in interval notation, we take the smallest possible value that x could be, which is a, and since x can actually be equal to a, we use a bracket, and then we write the largest possible value that x could be, which means it goes up to b, and since b is included, we again use the bracket. Second case is called an open interval, and this is where the endpoints are not included in the solution. So as an inequality, we have a is less than x, which is less than b, which means x is between a and b but cannot be equal to either of those endpoints. The only thing that changes in our graph is that we now use parentheses at a and b, showing that this graph gets really, really close to a, but never includes a, and really, really close to b, but never includes b, so we're using parentheses. As an interval, again, the only thing that's changing is instead of the brackets that showed inclusion, we have parentheses which show that we're not including the endpoints, but the order, a and b, is still the same order that you see on the graph, from smaller to bigger. Now we could have an interval that's considered either half open or half closed, and this is when only one of the endpoints is included and the other is not. So this is one case where we can certainly have the equal to on the a instead of the b. So here as an inequality, we have a is less than x, which is less than or equal to b. And the picture, notice again, the parentheses at a, the bracket at b, the shading is in between. The interval gets read right from the graph, so at a we're using parentheses because that's not included in the solution set, and b has a bracket because it is included. Now in this video and in this section, we'll be talking about simple inequalities. So we'll have one inequality symbol, which means that the other side of that inequality, or the other side of that solution set, is going to go out to either positive or negative infinity. And this gives us an infinite interval. So once again here, a and b are real numbers, x is the variable. And there are several cases. These are just one example from each case. So the first case, we have the inequality x is less than or equal to a, and this could easily be a less than a instead of a less than or equal to. But if we look at the picture, we're including a, so we see a bracket, and we want to take all of the values that are less than a as part of our solution. So that's everything on the number line that's to the left of a, and notice the arrows on the end of our shading to show that our shading is going to continue indefinitely. Now as an interval, we're still thinking about writing the smallest value and then the largest value. But here we never attain a smallest value because this keeps going indefinitely. Now to represent that, we write negative infinity. Now negative infinity is not an actual number that we can get to, it's more of an idea. So we use parentheses around negative infinity to show that we are going towards that, but we of course never actually make it there. Now in this example, a is included, so we have the bracket, but we could have a similar example that's just strictly less than, where we would have parentheses around the a. Now the next example goes in the opposite direction, so here x is greater than b. Now we're taking all values that are larger than b, so on the number line those are values that are to the right of b. Since in this particular case b is not included, we're using parentheses, but b certainly could be included if we had greater than or equal to here. Now here we do have a smallest value, or we can get up to the smallest value b, but not including it, so we have parentheses around the b. But there's no largest value. This goes out to positive infinity. And again, since we never actually get to positive infinity, it's not an actual number, we use the parentheses around the infinity symbol. Now a couple of takeaway points here. Always remember that when you're using interval notation, that the two values written in the interval go from least to greatest. So the smallest one gets written first, the largest one gets written second. Always use brackets for less than or equal to and greater than or equal to, and always use parentheses for less than, greater than, and positive or negative infinity. Now that's not the only way that we can represent a set or a solution set. So we have a more formal notation called set builder notation, and it has this basic structure that you see here. So we have our set notation brackets and some other language. So just reading this, we would say the set of all x such that x is a real number, and then of course we would have to describe x a little bit further. Most of the time we use an inequality to do that. So for example, x such that x is an element of the real numbers and x is less than 8. So we can imagine what that graph would look like. We would have parentheses at 8 and the shading would be to the left. Now when we're solving inequalities in one variable, our goal is the same as it was when we had equations. So we want to isolate the variable. We have the same addition property of equality where we can add or subtract to both sides, but the multiplication property changes a little bit, and this is our big exception. If you multiply or divide an inequality by a negative number, you must change the direction of the inequality symbol. So here we have a very basic example. Negative 5x is greater than or equal to 30. Now if we were solving for x, we would divide by negative 5 on both sides. But since we're dividing by a negative, once we write our next line, we're changing the direction of the inequality from greater than or equal to less than or equal to. So it just gets flipped around the other direction. So here we have x is less than or equal to negative 6. And you could certainly practice graphing that solution set, writing it as an interval, and of course writing it in set builder notation. Alright, so that concludes our notes about solving linear inequalities in one variable. So I urge you to take a look at some of the examples that you have in your text and practice those.